Okay, so I guess it's time, Michael. I'll start.
Absolutely, Tajinder.
Great.
You hand over, just introduce Anthony, and then we're away.
Great.
Yeah.
So, good evening, everyone. Good morning, good afternoon. And we are really happy to welcome Anthony Lasenby to give the 17th OSMU lecture on geometric algebra, octonions, and the standard model. Anthony is professor of astrophysics and cosmology at the Cavendish Laboratory of the University of Cambridge, and he's also at the Kavli Institute of Cosmology in Cambridge. Anthony has very wide-ranging research interests, which include anisotropy of the microwave background, cosmology in general, the galactic center, telescope surface profile measurements, phase construction problems, atmospheric spectral line broadening, geometric algebras, and the application of Clifford algebras in physics. It is indeed rare to come across a physicist who has worked on such a broad range of topics and contributed to them significantly. Anthony began his astronomy career with a PhD at Jodrell Bank, specializing in the cosmic microwave background, which has been a major subject of his research ever since. After a brief period at the National Radio Astronomy Observatory in the US, he moved from Manchester to Cambridge in 1984, where he has been since. His introduction to geometric algebra came in 1988 from the work of David Hestenes for the first time, and since then he has been developing geometric algebra techniques and applying them in research in many areas. Together with Chris Doran in 2003, he wrote the highly successful book Geometric Algebra for Physicists, which is recommended reading for anyone interested in the subject. Anthony has authored or co-authored over 400 papers and is also a member of the Planck collaboration. His joint work on efficient computation of CMB anisotropies in closed FRW universes has been cited over 4,000 times. The breadth and scope of his research is formidable indeed, and I think it's quite amazing that coming from an astrophysics and cosmology background, he's now exploring the significance of geometric algebra for the standard model of particle physics and for gravity. Very happy to have you with us, Anthony. Over to you.
Well, thank you very much, Tajinder, and thanks to the organisers, yourself and Michael, for the invitation to take part in this series and for organising the whole series, which has been very interesting. So today I'm going to speak about a different aspect of octonions and their relation with physics than has been spoken about before in this series. I'm going to talk about using a mathematical approach called geometric algebra, or GA. And this provides a language in which we can work directly with geometric objects, that is points, lines, planes, and so on, and then combine them algebraically with the Clifford product. And many aspects of mathematical physics become simpler in this approach. And I believe that it provides a unified language which one can use to replace other tools in physics, covering the whole range: vector analysis, complex analysis, quaternions, matrices, spinors, tensor calculus, and so on, which each on its own only provides a partial coverage. And just to respond to something that Tajinder was saying in his introduction, I believe myself it's because I've been able to use geometric algebra that I've been able to work in several different areas, becoming more theoretical with time, because geometric algebra provides a route in to these things that is very efficient, because it's only the one system you need. So clearly physics and geometry are intimately tied together in the fundamental forces of nature. We believe these originate in the local gauging of global symmetries. And what geometric algebra can do is tie together the geometrical elements that the symmetry groups refer to with an underlying Clifford algebra framework. And that, for example, encompasses the spinors and the wave functions of quantum mechanics in space-time. Both the operators and things they operate on in all of this all belong to the same algebra. In particular, I'm going to show how octonions can be realized in the space-time algebra, the SDA, which is the geometric algebra of four-dimensional space-time. Now, one of the things I've particularly liked about this series is that there's been time for people giving talks to expand a little on the philosophy that they bring to bear on thinking about how nature works. So just a little bit of my own philosophy here. So given how important Octonions may be in defining the symmetry groups underlying the standard model, and the success of the space-time algebra elsewhere in dealing with electromagnetism and gravity, which I will both discuss briefly today, then this suggests a question. Is the STA itself enough to get to all the laws of physics? And to me, this would have an overwhelming good feature. This is that we only know about 4 dimensions existing, and we know what metric it satisfies, 1, 3, or 3, 1, as a matter of choice. So the GA of such a space, i.e. space-time, seems a truly minimal way of approaching physical laws. And certainly it's at least a good place to start, and we can see how far we get. Okay, so continuing with the overview, I haven't got much time to cover a lot of possible ground today, but I'd like to convince you of the basics. So I'm going to give you a short introduction to the STA, and then show briefly how it works with electromagnetism, Dirac spinors, and gravity. And something that crops up in several places, this is a sort of sub-theme, is that using the STA, we're already supplied with objects at square root of -1. Are these enough to mean we no longer need to employ complex numbers as a separate category? So in this approach, we are actually interested in preserving reality for as long as possible and see if we're going to be forced to bring in sort of uninterpreted complex numbers. And we'll see that we can get more or less through to the end without them. But in the application of Octonions to the standard model and also to larger exceptional groups, there are some open questions which I'll highlight and bring forward a solution that may be of interest. And just to say generally, there's more details of the approach here in this paper, which is published in Mathematical Methods of Applied Sciences last year. The details are there. There's an archive version as well, which I should update to the published version. And hopefully there'll be another paper with a good deal more shortly. Just like to give some acknowledgements here. I'm a fairly late comer to the field of Octonions and have a big debt to many people who blazed a trail. And I'd like to thank in particular Cole Fury, Robert Wilson, Tevi Andre, Corinne Minogue, Tadinja, and many others for inspiring papers and contributions, which form the background to what I'm talking about. Okay, so let's start on geometric algebra. Start very simply. Consider a vector space with the usual inner product A dot B. We can then introduce a new outer or wedge product, which produces a new quantity called a bivector A wedge B. And the dramatic step, I mean, Grassmann already took the step of introducing A wedge B. The dramatic step is what Clifford did of combining these in a single geometric product, AB, which is the sum of this scalar bit and this bivector bit here. And the very interesting thing about this is that unlike the inner and outer products, this product is invertible. I could multiply an A to the -1 in from the left, and A to the -1 exists, and I can just use it like that algebraically. So what this leads to is that we now think of this geometric product as primary, and we derive the inner and outer products from it. The inner product is the, if you like, the anticommutator of A and B, is written there. The wedge product, naturally, because it's depends, it's antisymmetric in A and B, is here, half AB minus BA. And that forms the basis for an axiomatic development. The geometric picture of this is that we can think of scalars as being like points, vectors, directed line segments, bivectors, like A wedge B, is sweeping out B along A, or we could sweep out A along B. That would result in different orientations. And so we think of a bivector as an oriented area. And that's an idea which extends through to any number of dimensions, of course, because you've always got the direction of the plane that sits between A and B and sit on. It's only in 3 dimensions by chance that you have a single vector orthogonal to A and B, which is why we got the cross product. But that doesn't survive into higher dimensions because you've got, for example, in 4 dimensions, you've got 2 directions which are perpendicular to 2 other vectors. And then you can carry on going with trivectors and so on, where we sweep out by further vectors. Now, the key thing I want to get over is that reflections and rotations are very easy to implement in geometric algebra. And consider reflecting a vector A in a plane with unit normal n. And we know, if I just drop down here, maybe this isn't logically organized, but here's the answer that we know sort of conventionally, that we form the reflected vector by taking the starting vector and subtracting twice the projection of A on n. So A minus 2 n dot A n is the answer, written, as it were, conventionally. Actually, that's exactly the same as the output vector is minus n A n. And there's a little manipulation here, which I won't go through the detail of, but it just involves expanding out what we've already got. We know n where j is half na minus an. We know that n where j plus n dot a is equal to na. Those 2 facts together tell you that minus nan is indeed a minus 2 n dot an. And so this is very basic and useful. It's telling us that we reflect by sandwiching in unit vectors, and there's a minus sign that happens to come in. Now, it's a theorem, the Cartan-Giudoni theorem, I think effectively, that combination of 2 reflections is always a rotation. And so we can generate rotations via 2 reflections. We do them both like this, so the sandwiching gives us, because the 2 minuses cancel, that if we do it in a further vector m, we get mna nm. So notice we get the product here, and then the product in reverse order just there. And that's entirely general. We define a rotor R to be m times n, and then rotations are given by A goes to RA, R reverse. And that will just occur absolutely everywhere. It's not just vectors that do this, but everything, and is fundamental to the whole approach. And I just explaining again here, operation of reversion is reversing the order of products. And in fact, we could miss out the A, and then we'd find that R reverse equals 1, which is a hallmark of a rotor. Okay, so now we're going to specialize to the space-time algebra, the STA. And there we need 4 vectors, E0 and EI, I1, 2, 3. And we're going to take a signature of 1 and minus, minus, minus. And then they're all orthogonal. So in particular, I haven't noted it here, but being orthogonal, it means that the dot vanishes, but that means that in the geometric product, EI, EJ, or E mu, E nu, for different mu and nu, is the same as minus E nu, E mu, because I can just interchange them, but in doing that, because I'm only working with this part for orthogonal vectors, then it flips line. Okay, so that's the basic setup. What about bivectors here? I can form 6 combinations of 2 things from 4. There's 3 squaring to +1 and 3 squaring to -1. And these divide into space-like or Euclidean bivectors, which satisfy this. So I through j, I goes through 1 through 3, j the same. If I expand this out, as I said, I can write that EI, EJ, EI, EJ. Then the EI here is going to commute, or rather anti-commute through that EJ. And what I find is I get -1 out of that. And that generates rotations in a plane. Time-like Lorentz bivectors satisfy, let's do the same thing, but now with EJ replaced by E0. Again, this anti-commutes as it goes through. And even though E0 squared is +1, I've still got a -1 from there, and a minus overall from the flipping. And so I get +1. So space-like bivectors square to -1, time-like to +1, and they generate hyperbolic geometry. I can exponentiate E1, E0 with a parameter, and it's equal to this. And general Lorentz transformations, this is general in the sense they're both spatial and Booth, you can write them down immediately as R equals e to the b for b any general bivector. And just note that that means we have 6 degrees of freedom in the B, and therefore 6 degrees of freedom in R, which you can work out from what we've done so far is correct. Okay, next the pseudoscalar. So we define the pseudoscalar I. In any space, it's a product of all the basis vectors, which you see happening here. I won't go through the simple calculations attached, but basically it reverses to itself and squares to -1. And in fact, I anticommutes with vectors and trivectors in a space of even dimensions and always commutes with even grade elements. Now, in space-time, we can use it to write trivectors as dual vectors. For example, E1, E2, E3 is -I, E0 is E0, I. And then there's another 4 going with I times the EI. So at this point, sorry, I used the wrong thing. So at this point, we settle on a given fixed Cartesian frame vectors in which do the physics. We can think of this as a laboratory frame and rename our E mu to be gamma mu. And now we have available the basic tool for relativistic physics, the STA. Here's what it contains. It's got 1 scalar, 4 vectors, the gamma mu's, 6 bivectors, the products for different mu and u, 4 trivectors, the I gamma mu, and the pseudoscalar. So there's 16 elements overall. And we're using the new name for a preferred orthonormal frame. And that's because if you use this relation here, how they dot together to give them Minkowski metric, you see that they satisfy this anti-commutation relation, which of course is the hallmark of the Dirac matrix algebra. So hence that's why we call them gammas. But it's crucial to understand here, these gamma mu's are vectors in space-time, not a set of matrices in some abstract isospace. Now, each inertial frame defines a set of what we call relative vectors. These are space-time areas swept out while moving along the velocity vector of the frame. So gamma naught is the velocity vector of the lab frame. Let's take another orthogonal vector, gamma I, that's swept out here like that. That generates a bivector, which we call sigma I, which is gamma I times gamma naught. And it's easy to show from what we've already defined that they satisfy this algebra. Sigma I dot sigma j is delta ij, and half the commutator is the alternating symbol times I sigma k. Now, of course, these are defining relations of the Pauli algebra, hence why we call them sigmas. I've just written out the sigma matrices. I put hats on it to make it clear that these are matrices. And of course, this is also the geometric algebra, coming back to the GA version of the 3D relative space in the rest frame of the gamma naught. And a particularly nice feature is that this 3D relative space, one picked out as being orthogonal to gamma naught, it has the same volume element as the full space. You can work out sigma 1, sigma 2, sigma 3 is equal to the same as I that we had in space-time. You might like to look through how that works. So we have this picture here, which is a very convenient one. Here's the 4D space-time algebra again, and it drops down to 3D in this fashion here. The scalar is the same. The bivectors which square to +1 drop down to vectors here, which square to +1. The bivectors which square to -1, they become the new bivectors in the space, the 3D space. They all square to -1, and the I is the same. So this is our basic setup for doing 4D and 3D algebra. Now, of course, for physics, we also need a derivative operator. And if we introduce a reciprocal frames crop up a lot in geometric algebra. They're extremely useful. And what do we mean by it? I mean, a frame with an upstairs mu, a frame of vectors, okay, let's be clear about that, which dotted with the gamma mu downstairs give me this Kronecker delta. So I can derive the gamma mu from that. And then the vector derivative, this grad, is gamma mu d by dx mu, where that's an upstairs mu, which I can write it like that. And we can now do, for example, electromagnetism. We've got enough in place to do that. If we write F for an STA bivector, which we said has 6 degrees of freedom, then Maxwell's equations are grad F equals J, where J is the source current. And that's it. That's the whole of electromagnetism. Certainly the whole of the Maxwell equations, grad F equals J. And it's by far the simplest form of them that exists. If you want to, if you need to for a certain purpose, you can recover the standard form by writing F as being this bivector. You take the electric field components, you sum them with the sigma I, same for the magnetic field components, and you form F equals E plus IB, where I is the space-time pseudoscalar. So you've probably seen versions of electromagnetism in which the F, the Faraday, is some sort of version of E plus IB, where the I generally is some uninterpreted scalar imaginary. Here we find out what it is exactly. You need this thing to be the space-time pseudoscalar. And the advantage here is not merely notational. Just as the geometric product is invertible, unlike the separate dot and wedge product, the geometric product with the vector derivative is invertible via Green's functions, where the separate divergence and curl operations are not. And in fact, this suggests some useful new approaches to electromagnetic scattering and modeling, for example, for calculating the EM response of conductors to incoming plane waves. And this is just an example that Crestran and I and others worked on some years ago, collection of mirrors, a plane wave coming in from the left, and these are the scattered waves with full diffraction effects. Now, you might well think, well, I could do that anyway, given a conventional approach. The point about this was deriving a new, faster approach via this method. It was fast enough that you could change the direction of the input ray in real time, the input plane wave, I should say, in real time, and just have fun playing around, moving the source around. And we've worked on several things like that since. So another very nice thing in electromagnetism is that the transformation of fields happens by F goes to RF, R reverse, where R is a Lorentz rotor. Very easy to carry out. And it's a double-sided transformation. And that indicates, you can read off from this, sorry, using the wrong one again. You can read off from this that the RF, R reverse, that F behaves like that it's spin 1. Spinor type behavior, as we'll see in a moment, would be psi goes to R psi, as in the direct theory we now look at. Okay, so spinors develop a rotor at their left, like that. Objects like a Faraday change on both sides, like that. And the actual set of equations you get from this is really very simple. And again, I think this is by far the easiest way to carry out transformations of electromagnetic fields. Okay, so Dirac theory. Here this consists of all elements. The Dirac wave function consists of all elements of the even subalgebra of the STA. So there's 8 of them. And I've written here the 8 components out explicitly. It's rather nice that you can repackage these in this form. This is due to David Hessner's. There's a rotor that's got 6 degrees of freedom, a scale factor rho, we write it as rho to the half, and then a space-time duality factor e to the I beta over 2. So 1 degree of freedom there, 1 there, and 6 there. And here is the Dirac equation in the form first proposed by David Hessner's. Grad psi as sigma 3 minus EA psi equals M psi gamma naught. A is the vector potential satisfying grad wedge A is F. So over here, this is the most important bit, it combines the GA grad with the GA psi in the simplest way possible. In particular, the equation for a massless free particle, approximately speaking a neutrino, is then just grad psi equals naught, which is extremely reminiscent of the sourceless Maxwell equation, grad F equals 0. And again, I think this is about the simplest thing you could imagine doing. So in this approach, what's happened to the Dirac matrices and to commutative scalar I? So the Dirac matrices, a version of the action on them and some state, written in quantum form, will be like this. And here, what happens, we take the even psi, the even element of the Dirac algebra, and we sandwich it like this, a gamma naught on the right and a gamma mu on the left. And the point is that doing that keeps it in the even subalgebra. What about the imaginary? If we go back here, it's actually this I sigma 3 on the right. And this clearly squares to -1. And the crucial thing also is, if I just go back to the equation again, there's nothing on the right of this wave function psi. There's a gamma naught on the right of this, but an I sigma 3 can pass through it because it commutes with gamma naught. And so it commutes with the quantities at the right in the Dirac equation, which means that it can be protected from space-time transformations and also functions as well as an imaginary, since these operate to the left of the wave function. Okay, if S is another Lorentz rotor expressing a space-time transformation, then the rotor R in the Dirac wave function goes to SR, and that does space-time transformations. And meanwhile, the I sigma 3, because it's to the right, doesn't see any of that. So we can get observables by a double-sided application of psi. Two observables which are worth noting immediately are the current J, which is psi gamma naught psi reverse, and that boils down to rho R gamma naught R reverse, and this thing here we can think of as the velocity of the particle, rho v. And the spin vector is psi gamma 3 psi reverse, and again that goes to rho R gamma 3 R reverse. And the picture this leads to, and of course this then sets one's mind thinking about possible interpretations of quantum mechanics, we can think of the rotor in psi rotating the fixed gamma mu frame, shown here, to a new body frame in the particle, where the J equals rho v is the current, and v the particle velocity, S is a spin vector, and this E1 and E2, which are results of rotating gamma 1 and gamma 2, they're basically showing you the phase because you rotate round between them with I sigma 3. Now, if you insert this current into div of J, the divergence, and use the Dirac equation, you soon find you get 0, where the current J is conserved. And that happens whether there's an A there or not. And also, the time-lag component of J is positive definite. And explicitly, if used later, let's work that out. Gamma naught dot J is gamma naught times psi gamma naught psi reverse. And I'm putting these little angle brackets at each side to indicate to take the scalar part of, which this dot here is meaning. And in fact, that's a sum of 8 squares. The 8 things squared are the coefficients of the spinor psi in terms of the SDA even elements, i.e. gamma naught dot J is this set of 8 things squared. We'll come back to that later. It's interpreted as a probability density because of these properties we've just gone through. And a normalized wave function has a spatial integral of J naught equals 1. Conservation of J implies that the probability density flows along non-intersecting streamlines, which is very useful for visualization. In fact, it gives you a whole new way of looking at quantum mechanics, but not time to discuss that today. Okay, so then finally, before Octonions, I want to discuss the transition from global symmetries to local ones and the emergence of forces in the context of electromagnetism and gravity. And I'll use this to introduce the approach that we have to gravity, because I think figuring out how to include gravity is something which many people interested in understanding the standard model want to know how this might fit in. I'm only going to look at this schematically, but I think it's useful in terms of what happens later. And the SDA approach is to start from the Dirac equation in both cases, electromagnetism and gravity. And space-time transformations, as we've said, operate to the left of the wave function, and internal transformations operate to the right. So a global phase change here is possible at the right of psi, as we said, due to the unit imaginary commuting gamma naught and I sigma 3. You make that local, you get a corresponding covariant derivative, and of course this provides the A field we've already written in the equation. So that was at the right, and it was limited. We'll see how it expands a bit later, but it was limited to just this in what we did to get electromagnetism. So why don't we ask for the same for transformations at the left? We can ask for covariance under space-time rotors at the left of the wave function, and there's no blockage to these being general Lorentz transformations because there's nothing in the way at the left. And when made local, this leads to a bivector connection field in the covariant derivative. And this is a bivector valued function of a vector argument, and we call it omega of A. A is the vector argument. And similarly, we can ask for covariance under arbitrary displacements in space-time position. So just to be clear, the two things we're gauging are space-time rotations and space-time translations. And that turns out to lead to a vector-valued function of a vector argument. We call that function h of A. Now, I don't want to go through these details in any depth. This is just to give you a bit of orientation. But the covariant derivative in the A direction is this curly dA, which is A dot grad plus omega A cross. And the cross is the GA commutator product. A cross B is a half AB minus BA. And this has nice properties. It turns out that the properties of the cross operator, basically it satisfies the Jacobi identity, together with the fact that omega A is a bivector, means that this combination, let's just go back to it, this combination of this scalar A dot grad and the bivector cross bit here, it's not at all obvious when you first try or think about it, but it's true. This curly D sub A is a scalar operator and satisfies the Leibniz rules for derivatives. So you can use it as a scalar derivative any way you like in your equations. And then you get the full vector covariant derivative via this curly D is H of a partial dA curly D sub A. Now, what's this? Again, I just want to use it in a moment for something else. I will define it briefly. It's the multivector derivative with respect to A. And basically, we use the reciprocal frame again. We write A as A superscript mu, E mu, and form a reciprocal frame to the E mu to form a multivector derivative, E mu d by dA mu. Okay, so that's what it is. It's very useful because what these assemble to is something that's frame independent. I should have put this on the slide probably. This object, why I've done all this, is because what you end up with is something that knows nothing about coordinate systems. And you can carry out any coordinate transformations and set up new bases in any way you like, you'll still get the same results. So the field strength tensor has got the usual way by commuting covariant derivatives. It works out very nicely. We commute on some multivector M, and what you get is a Riemann tensor with the commutator product with M. And you can read off from this what the Riemann tensor is. I won't go through the details, and then make a covariant version of this with all the transformation properties you would want by inserting an extra H just here. The point I actually wanted to make, which is useful for later, is that what you end up with is something that's a bivector valued. You can see this object here is a bivector because the commutator of two bivectors is always a bivector. It's a bivector valued function of a bivector, and bear that in mind for later. And it's worth showing an explicit example of the Riemann, the one for Schwarzschild black holes, just to show the incredible compactness of the formulae you get from this approach. So this is a Schwarzschild black hole, and this function of a bivector is this bivector here that comes out, m is the mass, r the distance, and sigma r is a unit spatial bivector in the radial direction. M is the mass of the black hole. So this is very compact, right? All we do is return B, this is the working bit, plus 3 sigma r B sigma r. This sandwiching always preserves the grade of what you put in, which is why you get another bivector out. As an aside, even more impressive is one for the Kerr solution, which I've shown here. All you need to do to get the Kerr solution Riemann from this is make R goes to R plus IL cos theta. I is the space-time pseudoscalar. L is the angular momentum parameter of the black hole. And in fact, this does explain the complex structure previously noticed in the curve solution, but it does it in terms of the space-time pseudoscalar I. It was a bit like when we had E plus IB for the Faraday. For us, that has to be the space-time pseudoscalar, and the same here. Now, going back to the general case, you can define an invariant Ricci scalar, like this, use it in your Lagrangian for gravity in this form here, and then you find the equations of motion are incredibly simple. dA R of A wedge B is 0, and then the d wedge H of A is 0. Pretty simple. And basically, locally, this theory reproduces the predictions of an extension of general relativity known as Einstein-Cartan theory that's come up a few times in these lectures. It actually differs on global issues such as the nature of horizons and topology, basically because it's in a flat space-time, and further details and full description are in this paper here. So just want to emphasize a couple of things. We have gauged space-time rotations and displacements and thereby ended up with a gauge theory of gravitation in flat space-time. We call this approach gauge theory gravity for gauge GTG for gauge theory gravity, and its advantages, there's a little list of them here. Basically, you know what you're doing with observables because they're the things that are gauge invariant. It works in a flat space-time. You don't need, if you're trying to do it on a computer program, you don't need any tensor calculus package or any extension to curved space. You just do it as Clifford algebra in space-time. And it articulates very well the Dirac equation, since that was our starting point. Now, again, in the context of things that have come up in this series of lectures a few times, let's ask, is the correct theory of gravity just based on local invariance under rotations and translations, or is there something more? I personally think that scale invariance, the ability to carry out an arbitrary rescaling of lengths at each point, should be a further invariance of gravity. So think of it as dilation invariance. And in fact, we now have a new gravity theory where all the elements of the Lagrangian are indeed invariant under scale changes. That inevitably produces torsion. This d wedge H of A equation generalizes when you do this to d wedge H of A equals S on the H of A, where S of A is the torsion. And I believe that this torsion and the scale invariant nature of the theory could be crucial in understanding actually the cosmological constant, which is, I'm basically a cosmologist, so I'm extremely interested in anything that could explain the cosmological constant. And it turns out that models based upon this type of approach, they lead at late times to a constant time-like tension of the form I've written it here in geometric algebra terms. You get a time-like trivector, you dot A with it, that gives you a bivector. Q is just a scalar constant. This can provide a late-time dynamical effect in cosmology, which precisely mimics the effects of an external vacuum energy, but it's just an inbuilt feature of gravity. And there's a couple of papers at the bottom there which explain some of this. Okay, so finally, we make it to Octonions. And just so we're all on the same page at the start of this, of course, we know that the Octonions, quaternions, complex numbers, and real numbers form the only possible norm division algebras. And that as you go up from real numbers to octonions, you lose various properties. And you end up at the octonions which are neither commutative nor associative, i.e. AB times C is not, in general, the same as A times B, C. And so you might think, well, how on earth are we going to represent this using geometric algebra? Because it differs so fundamentally from the geometric product of GA, which is certainly associative. Well, we're going to use the STA, and we're going to divide STA Dirac spinors into parts that commute or anti-commute with the unit time-like vector gamma naught. And we can use these two parts, which are the Pauli and non-Pauli parts of the Dirac spinor, in a way which defines the octonionic product of two Dirac spinors in terms of the subparts. So we know an STA spinner has 8 real degrees of freedom, and so we're able to identify an octonion directly with a direct spinner. And so for an octonion psi, we define these subparts like this. Psi plus is a half psi plus a reflection in gamma naught of psi, and psi minus is the same but with a minus here. And these indeed then correspond, when you work these out, to the even and odd parts of the full 3D Pauli algebra and the usual space-time split correspondence between the Pauli and Dirac geometric algebras, which we talked about earlier. So here's our psi plus and psi minus derived from a single Dirac spinner. And here's the crucial result. Given two octonions, psi and phi, the octonionic product between them, which I'm going to note with a star, is the Dirac spanner theta given by this formula. So theta, which is psi star phi, is given by psi plus phi minus reverse psi minus plus phi minus psi plus psi minus phi plus reverse. I went through that sort of calling out each bit because I want you to see the detail on this right-hand side. I want you to see that actually every operation here is an STA operation. Okay, this product here between these parts is an STA operation. The reverse is an STA operation. And the same applies to all of them. Hence our claim about being able to compute everything entirely within the STA. These are all STA products, reversions, and elements. Now, from the form of this, you can see such a product is highly unlikely to be associative, and of course, in general, it is not. And the property it does have, however, comes from the essentially defining property of the octonions, that they form a normed division algebra. So we need to define the norm, and for that we need to define a conjugate element. And for us, this is, I'm using star to denote conjugation, it's psi plus reverse minus psi minus. And the tilde over the first term indicates usual GA reversion. So we do that. We form the octonionic product with psi to get the norm, and you can work it out. And it comes to this, comes to 1/2 gamma naught psi reverse plus psi gamma naught psi reverse gamma naught. And we recognize that. That's, of course, the time-like component of the Dirac current. So this is very interesting. It actually surprised me a great deal when I first arrived this, because I hadn't seen something like this before. We know from its interpretation as a probability current that J is always non-zero and future pointing as long as psi is non-zero. So along with its scalar nature and the sense of the grades present, this coincides perfectly with the properties a norm should have, right? Because we've got something that's always positive as long as your input object is non-zero. The other property we need for our product and norm to be representing a norm division algebra is the fundamental relation that the norm respects multiplication. And in particular, we want the norm of the product to be the product of the norms for all the Dirac spinors sine phi. And given our definition so far, this is a matter of computation, and you can find it does indeed work. And we can put this, in fact, in quite a nice way. Given our reinterpretation of the octonionic norm in terms of the Dirac current, we can write this result in a wholly STA form where, okay, we've got octonion multiplication here to define a theta, but what it boils down to is that the norm of a state psi times a norm of a Dirac state phi is equal to the norm of the octonionic product state as shown just here. This is pretty interesting because in this form you make direct contact with the paper from 1845 in which John Graves first introduced the octonions. I'm sure many of you know this. In this paper, it was about something completely different. He introduced what are effectively octonions in a PS to the paper, and this was the result he was interested in and wanted to communicate. This result is that the product of two sums of 8 squares is a sum of 8 squares. And that's exactly what we've got here, because we saw earlier the Dirac time-like component of the current is the sum of 8 squares. So we've got 8 squares here, 8 squares here, and what we found out is that is indeed the sum of another 8 squares from there. I find it fascinating to see a link here between this result from 1845 and Dirac spinors dating from over 80 years later. Now, we have to settle on some practical details, including a particular choice in the multiplication table for the Octonions. I've got one here. This corresponds to the one given in the very useful review by John Byers. It's also that used by Cole-Fury. And references to papers in general, I've put them at the end of the talk. When I get there, I'll try and make sure to display the page for a little bit so it's at least preserved on the recording. Now, this table, there's actually another 479 possibilities for it. So it's actually probably more illuminating to consider the Fano plane representation. And on this, I'm explicitly displaying the assignment of Octonion units to STA elements. So the way I'm doing this, so on the right in each of these is the STA element. On the left in each assignment is the octonionic unit. And I've settled on an assignment which gives a central position to the pseudoscalar I and treats the Pauli even and odd elements symmetrically. So the Pauli odd ones, the sigmas, are at the triangle vertices, and the Pauli even ones are on the circle. So that's the assignment we're going to use. Now we come to the fundamental forces. I'm just going to have a sip of tea. Not my voice. So the standard model of particle physics, as we all know, appears to work with the direct product groups SU3 cross SU2 cross U1. Can we find these, or perhaps some larger unification group from some general principle? And of course, most of you will know very well that what Octonions have to offer, or some aspects of what Octonions have to offer in this direction. So Cole and others have particularly emphasized the role of chains of Octonion operators. And this is a clever technique where you use sequences of Octonions to pack in a great deal more information, despite the relatively small size of the spaces involved. And non-associativity is crucial here, because the fact that A applied to the beginning sequence B phi is different from AB applied to phi. That means that you can get in more information, because how you built up the sequence matters. And the possibilities increase as we go to longer sequences, rather like a code. However, this process doesn't go on forever. And there's a nice explanation of this in the book by Conway and Smith. Here is the reference to it. And they show that 7 left multiplications, or 7 right multiplications, if you're building up the chains on the right, is the maximum you need to consider. And indeed, one will be equivalent to the other. And they explain this in the section, 7 rights can make a left. This means if you consider purely left multiplications, then you should consider sequences for a maximum of 6 of these. And Cole-Fury and others show this is isomorphic to the Clifford algebra CL06, where all the elements square to -1, and of course, sorry, all the grade 1 objects square to -1, and they're anti-commuting. Now, that much probably most people know. Let's show you a different view on this. That this happens, we can understand quite well from the STA viewpoint. And in fact, I'm going to do this by looking at right multiplications. I've recently understood that the structure of our product makes it easiest to translate into STA if you consider chains on the right. And then the STA translations of multiplying on the right by unit EI are as follows. For if it's I sigma 1, I sigma 2, I sigma 3, in our assignments, that's I is 1, 2, and 4, you reflect psi and gamma naught and multiply on the right by EI. If it's one of the sigmas, that's for 3, 5, or 6, again, you reflect in gamma naught and multiply on the left. And if it's E7, you just multiply by a -I, which says it commutes, doesn't matter which side. So this is really simple as the basic action of these, of multiplying, doing an element in a chain on the right. And now you can read off the fact of why does this form a Clifford algebra, more or less by eye. So let's just take one example. Suppose I want to apply I sigma 1 twice. So the second time I put it, there's a gamma naught EI, then gamma naught EI again, where the EI is the I sigma 1. And the point is that the gamma naught I get just here passes through the I sigma I there, because it commutes. And then I just have EI squared, which is -1. So doing it twice is -1. If you, on these ones, if you do a sigma I twice, then they square to +1, but on the other hand, they anticommute when they have to pass, when the gamma naught has to pass through them. And so that's how they both end up squaring to -1, even though intrinsically one squares to -1, one squares to +1. And proving anti-commutativity goes similarly. You might like to look at that. And so we really do have that when we put two elements on the right, like this, then if they're the same, we flip the sign. Otherwise, we get that the anticommutator is 0. So these are the defining relations for unit vectors in Clifford algebra. And as we build up the chains of these multiplications, we're building up planes in the algebra of CL06. Now, each of these is a defined map of an STA even grade element, a spinor, to a new spinor. And so we've got a 4D Clifford algebra acting on itself, the STA, with a total of 16 elements, and we've generated a 6D Clifford algebra with 64 elements. So what can we start doing with this? And now, one of the first things I looked at is that I discovered that there's a largest subset of commuting elements. We would think of this in terms of a Cartan basis usually. And it's got 7 elements. And so we can look at these 7 elements, and in chain form, these are, I'm doing it on the left here. This is how I first wrote them down. It's exactly the same result on the right. There's 4 things that have 3 elements at the left in the chain, and then 3 things that have 4 things at the left. Now, they look very hard to interpret, but remarkably, and I'd say definitely exciting as regards the STA approach, is that when you express these in terms of STA operations, the 7 states is very simple. T1 from here is minus gamma naught phi gamma naught. T2, well, actually, these are just the reflections in the gammas, and 5, 6, and 7 are reflections in the sigmas. So, in fact, these are the 7 distinct reflections, I'll explain why that is, which can be carried out using unit STA elements. And we can use odd elements as well, since reflection in either even or odd elements preserves evenness. Why these the only states? We don't get extra states from using any versions including I, such as trying to reflect in I sigma I or I gamma I. Since I commutes with all even elements, you'll just get a change of sign, not a new state. So that's why you don't see the ones with I. And you can immediately see why all these states intercommute and give you this what will be a Cartan subalgebra. Because although you may get sign changes when 2 reflecting elements are interchanged, such as interchaining gamma naught and sigma 3, which anticommute, you'll get 2 such sign changes due to it happening each side of phi. This is a nice thing about reflections, and overall the operations will commute. So if we do treat this as a Cartan subalgebra and apply it to the other states, we find we've got a group with 63 dimensions in total of rank 7, and I've checked via studying the root system that we've recovered SU8. And I wanted to mention this because I'm not sure I've seen that other people studying this particular approach have come up with that group so far, but it is there. And it occupies quite a high position in this diagram I find very useful of the relationship of various important groups. So this is taken from Wikipedia. I've given the attribution at the bottom. And it's a subgroup tree starting with E8, the exceptional group of order 8 at the top. And we can see that SU8 is not far below it, sitting as a subgroup of either E7 or the orthogonal group of order 16. Now, tracking down from the SU8 we found, I've now identified explicitly all of the tree leading down through SU8 to O8. I'm doing it in a version with unit determinants, so that's SO8, then SO7, G2. G2 is the smallest exceptional group with 14 dimensions, and then has SU3 as a subgroup. So 2 things at this point. How does this downward chain of groups work? And secondly, we want to illustrate our general approach to which groups are important by going into some detail on SU3. So let's think about the general approach here. And I have a proposition for selecting what's going to be important. Here's a proposal. Nature is interested in transformations that preserve the time-like part of the SDA direct current. And this is, of course, instantiated by using Octonionic multiplication to represent operations upon states, since this will preserve the Octonionic norms, which we said are the same thing as the direct current time-like bit. Now, it's important here to make clear we're talking about internal rather than space-time transformations here. But the transformations we need are double-sided. So how is this going to work? And because before we could just put general transformations, we wanted to do them on the left. But here we're going to be using some double-sided internal transformations, and we need to understand how that's going to work. And think about it in relation to SU3, which is the first way, which is where I first started. So this was before I was thinking about Octonions and the STA, and it's a way of representing SU3 wholly in the STA. So what we're going to do is we're going to extend an ordinary direct spin of phi to be both a function of position x and a linear function of a bivector argument f. So phi is phi of f and x. And then looking at the SU3 in relation to color, the separate color fields then arise as, phi I is equal to phi on sigma I. These are you can think of these as the separate color fields, where the sigma I is the same ones we had before, gamma I, gamma naught. And they're the unit norm spatial vectors of the SDA in the usual way. So within the SDA, we write phi is a linear function of f, and of course it has a position dependence as well. And why I wanted to emphasize the Riemann tensor earlier is that that's got the same structure. That's except it's bivector instead of spinor valued. The Riemann is a bivector valued function of an input bivector, which it depends on linearly, together with a nonlinear dependence on position. Okay, so that's the aim. And now we ask for transformations of bivectors f and the STA that keep the Hermitian inner product of f with itself invariant. And you can see that this is the correct construction. Gamma naught f, because I haven't been through it, but Hermitian adjoint in STA is reversion followed by reflection on the time axis. And reversion for a bivector is just f goes to minus f. Here you can see the reflection in the time axis, the gamma naught sandwiching it. And as I say, f goes to minus f does the reversion. So how does this work? How do we keep these, that particular norm fixed? And I should say, as in so many things, the first person who started talking about this many years ago in terms of a double-sided action to understand SU3 was David Hestenes. So it wasn't really quite complete, and I got through to the full version about 2017. I'm not going to go through the details, but what you need to do is you need an multiplication on the left by sigma I, call that EI hat, little EI hat, a multiplication on the right by I sigma I, FI hat, and we claim the appropriate U3 generators as shown here. where you have 3 in each line. So you get 9 generators over U, which we expect for U3. And the very interesting feature, of course, is that multiplying by the sigmas on the left or the I sigmas on the right is exactly what we found back in the translation that I gave you for the right multiplications of Octonion chains. So although I didn't know it and David didn't know it when we worked on this, we were doing Octonions, which is very interesting. So that all fits in well. And we just note here that in this combination of the little e and the little f, we are doing double side transformations. So there's no doubt we need to cope with that. But how do we do that in the Dirac equation, for example, given that we're doing this on both sides, but we also want space-time transformations? Well, here's the key point. In this 5 f and x, then f is internal and it doesn't see space-time transformations at all. Thus, it's free to be acted on double-sidedly. Under an actual space-time Lorentz transformation rho to r, then the phi of f and x goes to r phi f and x, and so can respond covariantly, plus partake in Dirac-type equations with a grad at the left. So actually, this approach works pretty well, even though it's slightly novel to think of spinor functions linearly dependent on a bivector. I've tried to argue it's not so far from what we do with the Riemann. Okay. Well, if we want to go to a full octonionic approach where we keep this thing constant, not constant, unaffected by the transformations, then how do we do that? Well, a way of doing it immediately presents itself. We could use single-sided rotor transformations of psi, like psi goes to psi r, where r needs to be a spatial rotor. Now, let's be clear what we're doing here. We want to understand how to preserve this under changes in psi. And one of these would be if we put a spatial rotor on the right, then psi reverse will bring the spatial rotor reverse just there. That, because it's spatial, it can float through the gamma naught and then combine with the r, we'll get just here. So we have 3 things, the I sigma 1, I sigma 2, I sigma 3. These are SU2. They provide you immediately with SU2. And then you could consider instead an e to the I beta type transformation. That also floats through because I doesn't reverse. It doesn't reverse to its negative when you do this. So you still have an I here, but it anti-commutes with gamma naught. And so actually it commutes and you get a global U1 symmetry from that. So just by I, you can basically immediately see why SU3, SU2, and U1 might be picked out. And of course, there are many other transformations, including mixtures of these, which preserve that. Okay, so the covariance issue, we can extend to proper local gauging to make a proper gauge theory by now using phi, which before was a function of the bivector f and space-time possession. Now it's got to be a function of the Dirac spinor psi. And that psi is internal. The phi here will pick up space-time rotations at the left. Okay, so that's the recipe. Now let's return to the question about how the chain of groups from SU8 down to SU3 rises in our approach. There's quite a few details here. I want to do this fairly lightly. Basically, we had this Cartan subalgebra consisting of the 7 STA reflections. Let's supplement that with the identity. So now have 8 elements. We multiply these on the left with EI. This is a octonionic multiplication for I equals 1 to 7. If you discard the identity, we've got 56 states. Every single one of them is picked out by this process, which splits them into 7 sets of 8. Okay, so 56 goes to 7 sets of 8 via this. Furthermore, each set of 8 divides into 2 sets of 4 mutually commuting states. One of these subsets contains a simple state, EI star psi for I equals 1 to 7. That's the one we're going to use. So now we've got 7 sets, each with 4 things in it. Now, immediately, it's very nice, this. We've done this by working down from SU8. It may not be obvious, but these 28 objects immediately give us a basis for SO8. You can check explicitly that the multiplication table is correct. I'll come back to this, but if you discard now these EI psi states in each case, you've now got 7 groups of 3, and that's SO7. So we've reached that. We call these objects JMN, M is 1, 2, 3, N is 1 to 7, and the set of 3 for a given N are all mutually commuting, because we have 4, but we've thrown away one of them. And just a reminder, the M comes about by having discarded one of the 4. The 7 refers back to the 7 unit Octonions. And it turns out these JMN have simple definitions in STA terms as combinations of single elements and reflections. If you remember that E6 had the STA equivalent of sigma 2, so this is just an example, you find that the J's for the 6th N are sigma 2 in each case times a set of 3 reflections. So it really is simple in the STA. And we brought in the reflection operations we talked about as being crucial in SU8. Now, sorry, this looks a bit of a mess. What we're doing here, though, is now we define from these J's the following 14 quantities. The Fi is a half J1i minus J2i, I equals 1 to 7. Mi is this different set of differences added together for I equals 1 to 7. And the Fi for I 1 to 7 are the first 7 SU3 generators, while M7 provides the missing F8 for the 8th SU3 generators. The Mi left over, there's 6 of them. Once we've used M7 this way, we can use them to define quark states. And here's the equivalence with the Gell-Mann matrices. This shows how they line up. F8 is M7 is the same as the 8th Gell-Mann matrix. And then the quarks, now this is somewhere where it would be useful, and we'll come back to this, to bring in an explicit I, but the quarks then, in terms of, we're doing color here, you put them into ordered pairs. The red, a red quark and red antiquark are the pair M3 plus or minus M1. And here are the same thing for green and blue. So how do we interact? The gluons interacting with the quark-antiquark pair are the Fi acting on the states Mi, and they do it via the commutator product, which corresponds to the Lie bracket of a Lie group. So we're doing quantum mechanics, so the observables are the eigenvalues of operations, and you find that this indeed gives complete mapping of the color force onto this very limited set of particles that it's operating on. So that all works, but we have to use the notion of pairs of states in order to get through to the end. Now, we've seen how the 64 left states can give us SU8, and you drop down through this chain to reach SU3. How about the chain leading through the exceptional group F4 to SO9 and SO8? This would be very interesting, since F4 is associated with the Albert algebra, which is an exceptional Jordan algebra. And this is of great current interest in attempts to link with the standard model. For example, the Ginger himself is working on this, and several others looked at this. And a prevalent feature of these algebras is that they're usually represented by matrices over octonions. For example, this Albert algebra is the algebra of 3 by 3 emission matrices with octonion entries under the Jordan commutative product. What does it mean to have matrices over octonions, and what are the types of rules necessary to deal with the non-associativity? And these are questions which people have spent a lot of time on. So do we have anything to offer here? And as a fairly modest start, I'm going to consider how to go upwards from SO8 to SO9. And in this, I was helped a great deal by two papers. This paper here by Wilson, Gray, and Minogue, which appeared last year. And then very recently, which was also being discussed by Tevian in his recent talk, this paper here, a new division algebra representation of E6. And in these papers, we have as first steps leading up the chain eventually to E6 or E8 and transition from SO8 to SO9. So that's what I'm going to look at here. Now, but I should probably pause at this point to just ask how I'm doing on time and how much longer you think I can carry on.
One moment. So we are 10 minutes over, maybe another 10 to 15 minutes. Is it
okay? Yeah, okay. Hope everyone is still surviving at this point.
Yeah.
Okay, so the starting point for this is a set of 2x2 anti-Hermitian matrices over octonions. So this is straight from the Wilson et al. Paper. They introduce an x1 which behaves like this, and an xp like this, where p is one of 7 octonion units squaring to -1. And these matrices are meant to operate on column vectors of this form, where phi and psi are octonions. They don't explicitly spell out that construction, but they say this is what is happening. And we define from these two further quantities a dp, which is x1 with xp, which ends up looking like this, and a dpq, which is with q a different unit imaginary. It's equal to p circle q and p circle q on the diagonal. This is a commutator of left actions octonions. So basically, we can think of that as like pq minus qp. Now, what have these given us? The dp and dpq, there's 7 of those. There's 21 which come here from the two different things in p and q. And so we've got 28 quantities, and these obey the commutation relations of SO8. And then we are able to get to SO9, dimension 36, by adding in these x's. The x1 and the 7xp then give us something with 36 dimensions, which satisfy all the correct commutation relations for SO9. Now, is there an STA version of this? And in an attempt to translate this, I initially thought that the doubled up octonion column vector should be interpreted as something like this, a phi left side right, that the x1 matrix were then changed to give a psi left minus phi right. And this approach does in fact work, but it's somewhat redundant, and it's perhaps not very close to what we might hope for as an STA translation. And instead, a clue comes from noticing that the x1 matrix, just look at it again, is a version of the unit imaginary. We multiply it again by itself, we get -1. But of course, it clearly can't be a commutative imaginary. Otherwise, all the commutators with x1 would vanish and we'd be left with nothing. So what works is if the imaginary, whatever it is, anti-commutes with the unit octonions a negative square, i.e. the p's and q's. So if we call such an operator j, then we find the following assignments work. x1 equals minus j. Turns out xp is 1 plus j times p. dp is then 1 minus j times p. And we form the dpq. And it's quite nice because p anti-commutes through the j. We end up with this structure here, 1 minus j squared. And j squared is -1. And so a half times it's just 1. And we do indeed get an explicit pq minus qp for this dpq. It's really simple. So what could this j be? And we haven't got room for uninterpreted new symbols in the minimal STA approach. This object needs to square to -1 and anti-commute with E1 through E7. So a basis vector E8 would do very nicely for this. And what works well, and it also provides a solution for the unit imaginary, which had to be a commutative one that we needed for the Gell-Mann matrices on operating on quarks, is to bring in the Sedenians at this point. Now, Sedenians have cropped up 1 or 2 times in these talks. The 16-dimensional Sedenian algebra is the next algebra along generated by the Cayley-Dickson procedure after the Octonions. famously, the bit that fails here is they're not a division algebra. Two non-zero Sedenians can be multiplied to give 0. But as pointed out by Niels Kresnik and others, actually the algebra is being used by others in new approaches to the standard model, such as C cross O and CL6 itself, are not division algebras either. So it not being a division algebra is maybe a moot point. And certainly in the STA case, it's very appealing to extend to the Sedenians. And so far, we're only using half the available representation space. We're using all the space for operators, but in terms of representation, we're only using 8 components instead of the 16 actually available to us. And perhaps the best argument, and this is straight for Niels Kresnik's talk, is that the Clifford algebra structure that we found before with going up to 7 objects, in particular these 2 lines, you swap 2 things down to commute, you square something, it squares to -1. They don't extend to the full Sedenians, they do extend to the set where you adjoin E8, enabling a Clifford algebra approach on this extended set of objects. So actually, we found our J if we use E8. So can it be done in the STA? Yes, I've got a translation for the Sedenian algebra, which indeed uses the full set of 16 STA elements and just the usual STA products. So there is room for it, and it all works. And here's one of the possible multiplication tables. There's even more possibilities now generated using the STA approach. And if you have a chance to look at this at leisure at some point, I just invite you to look at the E8, E7, and E7, E8 columns and rows. And what you'll find is that E7 followed by E8 squares to -1, plus obviously it has to commute with the set E1 through E6, which formed the CL6 and gave us the 64 left multiplication states, which we use to represent SU8 and subgroups. So actually, going back to what we did there, we now have a commutative imaginary available in the space, which we can use to simulate the uninterpreted eye using virtually all other approaches. And we began to see was needed in dealing with the possible quark states. So there's 2 things. Just E8 as an imaginary, it's anti-commutative and squares to -1, which is what we wanted that J to be. And in fact, returning to SO9, we got to this point, x1 is -j, xp is 1 plus j times p, leading to this, gp is 1 minus jp. Actually, if this j is just going to be an E8, then it's pretty obvious what we should do is take the sum and difference of these x's and d's, in which case the 8 new entries in the basis, which we add on to the 28 for SO8, are now just E8 and combinations of E8 with the other EIs, up 1 up to 7. In other words, all we've done at the end of this, once we've got this E8, is to add an extra state to SO8. So of course, it goes up to SO7, extra orthogonal state, I should say. So this makes perfect sense. It's exactly what should happen. So I'm going to wrap up very shortly. According to the Wilson et al. Approach, the next step up from F4 to F4 from SO8, and we would like to get to F4, involves 3 copies of SO9, and this leads to the concept of triality. And of course, this is intimately involved in the F4 and the Albert algebra. Now, of course, we know we want to ultimately accommodate 3 generations of fermions, and maybe triality is to do with that. And indeed, maybe it's a good argument for using the Sedenians, because Niels Kresnik has made it very clear that they have a very nice version of triality which could be used in this form. I'm going to do something less ambitious and just look about standard triality, which happens when you consider the states due to left multiplication, right multiplication, and reflection multiplication. I'm not going to go through this bit in detail because I think time is definitely running out. I just want to show you what this leads to. Here we go. In terms of our thoughts about how we might get to Jordan algebras and how we might get through to F4. So I've mentioned, of course, several times the 64 states, the CL06. What maybe is not so clear is that you can set up things so that those transform on the left under 2 or more chain transformations. Say you had an E1 and an E2, they would give you, by the route we talked about before, a rotor, because they're 2 unit vectors and they give you the rotor R. Here we have reflections, 64 states just of reflections, and all commuting means that they're basically a Jordan algebra. Why do they commute? It's because reflections always have to commute, for what I said earlier. So this is where we put an EI on one side and EI on the other side, etc., and build up the chains both ways out. That transforms like this, and then we have right actions which transform like that. And these are the 3 things which crop up in the triality. And we have a Jordan algebra sitting here, which is available to us to see whether we can use it to give us the 27-dimensional Albert algebra. Is it embedded in that or not? And that's something I'm certainly very interested in. And just to emphasize, at this level, we haven't put the Sedenians in. This is all just based upon the initial 64 states. Now, these outside algebras, we said they work just via least sense with commutation. This middle one, that works by a commutative product. Let's adjoin on top of those left action with these 8 E8 states. Now we do adjoin the Sedenians, reflections with those, and right actions with those. And restrict in each column here to SO8, right? So we have 28 in each of those. And these at the top are genuinely independent. But I think the proposal, which is underlying the Wilson et al. And Drey et al. Approach, is that we take the extra piece from each, adding to the SO8 reflection column, like this, but we leave underneath, this is translating it into my term, just the reflections here, because then we'd get the 52 elements of F4. So the question is this how F4 works? And to do that, I have to work out whether these actions close, whether I can actually find out whether the group actions all give me closure. And that means doing this for the Sedenian states as well. I think it'd be quite interesting if underlying the attempts to move up to these higher exceptional groups, we do in fact need the Sedenians. And that's something I would like to get to the bottom of. So if this or something similar does work, we can probably rapidly work up the chain through the exceptional groups to reach E8. And with this commutative imaginary from the Sedenians, we need to return to the construction of Cole and others in terms of detailed matching to the standard model states. And the Jordan versus Lee setup we've got here could be very useful in this. I know that's another thing that arises a great deal in the current studies. So I hope to make progress with those soon. And I'll just show you, so it's on the recording at some point, a set of references on which give us some further reading. And with that, I say thank you very much. Thanks very much for your fortitude in getting to this point.
Great. Absolutely wonderful, Anthony. What an extraordinary lecture. Great that we have a recording for posterity. So we are open to questions now. So there's lots of comments in the chat field, but I would request if you could kindly raise your hand and whatever comments you made. Oh, there we go. Cole, please go ahead. Please unmute yourself and
try again.
Yeah, go ahead.
Took a couple of tries here. Thank you so much, Anthony, for a great talk. I've got a few questions, but I'll just start with one. So you chose this path going from SU8 eventually getting yourself down to SU3. And I was curious to know, did you try checking out the path going down to SU5? Because the whole standard model gauge group will fit inside of that. It might not get the representations right, but I was wondering if you check that out in this the Wikipedia diagram that you had put.
Yes, this one.
Yes. So did you try going through SU8 down to SU5?
That's a very interesting question. No, I haven't been down that route. It's certainly available to me.
Okay.
Now, SU5, of course, would be a great interest. I think I was particularly interested in G2 when I started, hence going over that route, because that quite explicitly enables you to combine the gluons with a quark in a single structure of 14 elements. But yeah, no, it's a very good point. I haven't tried that route through SU5.
Okay, thanks. I think other people have questions, so I'll save my other questions for later.
Okay.
Okay.
Thanks.
Davian?
So first of all, thank you for a very enjoyable talk with more details than I think you presented. But let me start with a couple of comments, and then I have a relatively small question. The first comment is that in some sense, our work shows that you can get from Octonions to Clifford algebras, and you're showing you can get from Clifford algebras to Octonions, which is a very nice alternate representation. Let me phrase it that way. The question that I want to ask comes back to your use way back in the beginning, where you were talking about making the vector associated with a spinor, which in standard language would be something like psi bar gamma mu psi. And you showed how to make that as a space-time algebra object. And I notice with interest that there's no bar. That this mysterious operation in traditional physics of barring a spinor isn't.
Okay, so there was the equivalent, because there was a psi reverse.
Yes, that's my question. Is reverse the role of bar?
You can think of it as having the role of bar. Yes, it's the closest to it. So that type of adjoint, the bar adjoint, is like taking a reverse, and that's obviously a covariant thing to do.
Yes.
At the level of you're not picking out a particular direction, is what I'm trying to say. Whereas the Hermitian adjoint, there you are picking out a direction. You're picking out the gamma naught direction, because that combines the bar bit, the reverse, with gamma naught reflection. So that's non-covariant if you're trying to do that on a space-time entity. And so one would certainly hope that it's the psi reverse which you pick up as the thing that is right for fully covariant expressions.
And let me thank you. That's what I suspected, but thank you for the confirmation. Let me finish with one last comment. Near the end, when you were talking about our X1 element, I would like to point out first that we did in fact choose it as our complex structure. That second, it commutes with our spinors, but not with the generators of our Clifford algebra.
Yeah.
And so that because of our type structure, we have both. That object commutes with some things and not with other things. And whether that's enough for what you want to do is not obvious.
Okay, I put it to the page where there's beginnings of a translation. And so I do believe that as long as you have an imaginary which anti-commutes with the P's and Q's, then you're in business and can do what you do. I think that agrees with what you just said, basically.
It does, but the subtlety is that for us, context is everything. It depends on which elements of E8 we are acting on.
Right. Now, of course, what I'm very much hoping is that the approach I'm outlining here, which is basically where this gets replaced by an E8. And I'm afraid that's a terrible name for it in some sense, because I don't mean the group, I mean E subscript 8, the eighth basis vector. That really makes things much more straightforward if it works. Because it's possible that's all I have to do to make this whole structure, which I'll show again, the possibility for F4. All I've got to do is employ a known multiplication table. I don't have to have the special rules for how the matrices behave when you're using them to simulate the octonionic type product, which, since it's not associative, is very tough for matrices. But you've got this very nice route through, which does enable you to use the matrices. But I think what I'm looking for in this STA approach is something that really is very simple, and all I have to do is say, okay, I've got this thing which is an element of the STA. This thing's an element of the STA. I combine them using an STA product, and that would be very good.
Agreed completely. Thank you.
Okay, great. Thanks. Ashutosh, please go ahead.
Okay, thank you. And thank you. I really appreciate this talk. I may be the experimentalist here in the audience. And when I say that I understood quite a bit of your talk, then maybe that's my way of saying what a nice talk it was. If you could go to the slide where I think you say Poincare group is gauged. I want to confirm if that's how torsion shows up as an additional equation in addition to Einstein's equation, which if correct me if I'm wrong, that only gauges the Lorentz group, but does not gauge the Poincare group. Is that correct?
Let me just find the relevant bit. Okay, yes, that's around here, isn't it?
Yes.
Okay, so what we've got here is a gauging of the, you can call it the Poincare group. And that's a way of thinking about the combination of the Lorentz rotations and these translations that I was talking about. That's how it gets to be Poincare. And we have two differences compared to what many people do. One is that we adopt, when we're taking the derivatives of the Lagrangian, the functional derivatives, in order to get the equations motion, we use a Palatini type approach in which connection is completely independent from you can think of it as the tetrad. The H function is like the tetrad, the omega function goes with the connection. And so we don't assume that one is given in terms of the other at the outset. It's just a Palatini type approach. And in that approach, you can then get this torsion arising. And it turns out to be integral, necessary to the equations once we've gone for scaling variance. We don't use, it's rather ironic actually, I'll just go back to the, here we are, here's the standard Einstein-Hilbert Lagrangian, which just uses the Ricci scalar. We use terms which are quadratic in these structures, so you can form a Riemann times a Riemann, and something quadratic like that has the correct properties under scale change to give an invariant in the Lagrangian. Basically, you need something of weight 4 to counteract this determinant just here. The Ricci scalar's only got weight 2. And so in fact, this on its own is a non-scale invariant, a Lagrangian. And it turns out to be, there's quite a few combinations of quadratic terms you can use, which have the correct weight, but you can't use this one. So this is sort of orthogonal gravity to Einstein gravity in that sense that you end up with when you're putting in scale invariants. And it's in that sense that you find you definitely need this torsion, and then it can suddenly have this extremely interesting role. The constant background cosmological torsion can actually drive the late time acceleration, which I find very nice. I don't need to worry about an external source for the cosmological constant. It's there in the gravity via the torsion.
Good. If I may ask a quick follow-on question. Let's see how I can phrase it. Maybe I'll come back. Why don't I come back, digest what you said, and then follow on so that somebody else can get a question in.
Thanks. Bernd, please go ahead.
Basically, it's a follow-up question to the previous question. So, is your torsion effect constant? Do you get a real constant, cosmological constant, or do you get cosmological terms that mimic a cosmological constant? Because there's, if you start with Einstein-Cartan theory, which has a linear Lagrange function, you can also get cosmological terms, but they depend on the spin density at a certain era of cosmological evolution.
Yes. So here we don't need any spin source. So that's different from Einstein-Cartan. Basically, Einstein-Cartan, as you know, has no propagating torsion. It can't just sit there existing independently of everything else. It needs a spin source. Now, of course, we could cope with spin sources in this approach if we needed to. But what we're talking about here is something that has no spin source. It's just happening that the torsion can exist independently of such a source in these types of theories. And it is not quite what happens as the universe comes out of some initial stage with a torsion, which can be, this background torsion can be at some quite different value. It's not required to have the value that it ends up at all. And it then gradually forces it, as time progresses, is very nice. It forces it to a constant. And so it's an asymptotic form of going to this constant. And I've shown the sort of final result here. So by today, in terms of the evolution of our universe, it's more or less constant. It's only much earlier on that you'd be able to see any effects from it not being constant.
Okay. So I would have a few follow-up questions, but now the second round starts with cold fury.
Yeah, Cole, go ahead, please.
Thanks. Everybody's being so polite today. Okay, so I was going to ask about, so you've got this neat way of being able to introduce the octonionic multiplication rules using entirely using kind of operations within the STA. I might have asked you this before, but do you have any sort of intuition? Like, how did you come up with it? And do you have sort of a geometric intuition for why this multiplication rule should pop out? Like, does it have a geometric meaning?
That's a good question. So I could probably answer the bit about how I come up with it, which is, all these things, as we know, basically stem from the Cayley-Dickson procedure. That's the way we move up. And so I was looking at how the Pauli spinners and the sort of odd, the even part of the Dirac subalgebra, which is represented by the Pauli spinners. And then we also have the odd part of the even subalgebra. So that's represented by these two things here. They're like quaternions. They're quaternions and then a sort of a different version of the quaternions, but with same four elements. And so if you look at the Cayley-Dickson procedure and you're trying to assemble things using the STA versions of the quaternions, then you can gradually see how you could create something which would sit properly, fully within the STA, but give you the Octonian product. So I shouldn't claim too much credit for the form here. You can arrive at it via the Cayley-Dickson procedure, but you have to be very careful in terms of the assignment to these subparts and in terms of what you call the psi plus and the psi minus. And the same thing happens with the Sidonians, except it turned out suddenly to be easier there. For the Sidonians, of course, I'm using two Octonions effectively, and one of them is then put into the odd space, But again, you have to be careful how you do the combination so you get the desired output. But that happened pretty quickly, whereas this one here took me a long time to make it work. And of course, when I found this, that the assignments I'd made and the way of doing it yielded the direct current, I suddenly felt, this is very interesting. I don't think I've seen that before. And this is suddenly telling me something about maybe there's a natural fit between the Octonions and the space-time algebra. And, the stuff about the 8 squares, I just found amazing that that's really saying something about the product of time-like parts of direct currents. So I can't really give you a terribly geometrical explanation, but that's roughly how it happened. And then I think the result is something interesting. It's not just a rewriting. We've actually understood something at the end.
Yeah, nice. Is it? Do you have any feeling for the uniqueness of it? Is this the only one that you've been able to find so far?
I'm sure there'd be a different version, for example, which would make the left chains simple.
Yes.
That would be quite nice, actually. It's ironic that it's turned out when I spent most of the time working on left chains and trying to decode what they look like, they're not as pretty as this. And all the time I should probably have been using right chains, but that must be a function of the choices I made in creating that product. There must be a different version of the product which will make the left chains nice. I don't know what that is at the moment.
Thank you.
Ashutosh, please go ahead.
Okay, thank you. So I think that previous conversation helps me frame my question. Do I understand correctly that if torsion was introduced in a way where it requires a spin source, then it would violate one of the conditions of the cosmological principle? And B, your way of introducing torsion via a scale invariance need not violate the cosmological principle. So it's two parts, A and B.
Yes. So let me think. Part A, you probably know that in Einstein-Cartan theory, which needs a spin source to produce torsion, you probably know there that the way they end up having to use it in cosmology is because you can't have a naked direction that would violate the cosmological principle. And so the way they introduce it is by averaging over possible spin sources to get something isotropic. And what you find is quite nice. I think these are called Weissenhoff fluids, where you do this, that you end up with something that, despite the averaging and despite being isotropic, still has an effect in the square of the spin. So you can use that in cosmology. And people have spent a lot of time trying to see if, for example, it can avoid an initial singularity. I fear that it actually, in general, it doesn't. It actually enhances the initial singularity. There have been some claims to the contrary. So that's point one. What we do here, there's no violation of the cosmological principle because it all, I won't bother going back to the expression, but the torsion is time-like. And so it's absolutely fine because there's no preferred spatial direction.
Okay, thank you.
On that note, Anthony, I could ask you a related question that if we think of spin strictly as a quantum feature having quantum origins, and then I think of torsion also as something quantum, and keep in mind that there's some similarity between the weak interaction and general relativity. Is there some insight on weak interaction and torsion being essentially the same physics?
Yes, I'm not sure about weak interaction and torsion. I think the analogy with gravity is quite nice in that, as I was saying, I don't know if I get the right spot. If I go along here, yes. So I emphasized that the SU2 appears to come out by psi goes to psi r, where r is a spatial rotor. Okay, so on the other hand, gravity came out by psi goes to r psi, so the other side, where r wasn't restricted though. It could be a full thing, including Lorentz transformations as well. So I think my answer to you is yes, I do see a strong link between SU2 and gravity, in that SU2 is like a restricted version of.
So can I think of SU2R has something to do with gravity? SU2L for the weak and SU2R for gravity?
Yes, I think I understand that. Yeah.
Okay.
I can see a link, but I haven't gone through that.
Yeah, I think I'll write to you about this. And then so maybe Bernd will take David first because he hasn't said anything. Go ahead, David.
Are you muted?
You're mute, is it? Okay, so I'm so
sorry.
Hey,
can you hear me now?
Yes.
Good. First of all, thank you for the lovely talk. My question was if you've thought about, or if you think it's possible to find a product for the split Octonions.
That's a very good question. I very much want to do that, because I think from all we've seen in terms of what people are doing, both in the standard model side and, linked with that going up to the exceptional groups, the split versions do look very interesting and important. And I haven't got them at the moment. So I would certainly be interested in seeking to do that. I'm hopeful that it is possible, but that's certainly on the list.
Great. Yeah, I'll just mention we found utility for 3 generations with the split Octonions.
Right. Yeah. Well, and they're pretty important in what Tavian and others do as well, that they emphasize how they use the split versions in making the link with E6, for example, and in the standard model versions.
Yeah. On that note, I wanted to add here, Anthony, that when you talk of using all the 16 elements of the STA and hence motivate the sedenion, an alternative to the sedenions could be the split bi-octonions, by which I mean O plus omega, O star, where star is the octonionic conjugate, and omega is the split complex number made from the octonionic units. It has the same properties. Omega square is 1, omega star is minus omega. So omega octonion plus omega O star is also 16-dimensional, and is very useful for me for defining chiral fermions. And I thought maybe if you think of the 16-dimensional STA somehow related to the split bi-octonion, that could be very interesting.
Right.
Do the 816 of STA in some good way come as 8 plus 8? Can I think in that way?
Yes, of course. So there is 8 plus 8, which I'm using in the Sedenions, and that you have the even subalgebra and the odd subalgebra. And
right. That could go well with the split bi-octonions.
Right.
Okay. Bernd, please go ahead.
Yeah, thank you. So I have 2 points. First of all, everything you said about the torsion is right. So you can use a Weissenhoff fluid, and in this case, there were some models where they try to show that you don't have a singularity, but you get an enhancement of a singularity if you use Dirac spinors as the source of torsion. Then torsion is also just attractive, and you get 2 sources of attractive gravity, and this makes the singularity problem actually worse. So but you seem to use a Lagrange function which is quadratic in torsion and curvature. Is that correct?
Yes.
Okay, so did you have a look at the particle spectrum? So how many graviton states do you have?
That's a good point. As I understand it at the moment, I have looked at this. I'm very happy that there are solutions which are do allow ordinary gravitons, which we need pretty much given the information we have from the gravitational wave observations,
yes,
the
of course.
coincidence in with the electromagnetic progenitors, and you've got to make sure you've got massless gravitons with two polarization states available to you. Now, what else there is in the theory is something that we're working on at the moment. We're trying to carry out an analysis of the particle content of the theory to make sure it's as healthy as it can be.
Yes, that would be the next question, because in many cases, if you use a quadratic torsion and curvature, you get some very unhealthy states.
Understand. And so we did a study of Poincare gauge theories. This is in a sort of fairly conventional approach. You can find it under Lin, Hobson, and Lasenby. I think we had 2 or 3 papers.
We'll have a look at it, okay.
Yeah, which actually tries to look at the particle content and the unitarity of these types of theories. And we were very happy with this, because the results from that pointed us towards a specific subset of theories and gave us relationships between the coefficients of the quadratic coefficients. The quadratic parts of the
coefficients for the quadratic vector, yes, which is also probably because they're undetermined at first.
Yes, so in complete general theory, you've got quite a few constants, extra constants, as these quadratic bits. But this starts tying down the relation between them. If you ask, absence of ghosts and unitarity. And so we looked at theories that Will Barker has been spearheading this. He's been looking at theories which are healthy from this point of view, at least as far as you can tell, and was led to the subset of theories that we've been looking at here, which are these ones which give you this cosmological constant.
Okay. That's double nice, though.
Yes. So actually, we're very hopeful that theories of this type are in fact going to be healthy, even though you're completely correct in the general massive theories where you could have all sorts of different values for these coupling constants. Of course, probably most of them will be unhealthy, but we're hopeful for this one.
But in a sense, then you can also exclude the coupling constant, so it is also helpful.
Yes.
Okay, then I would have this time not related to torsion, and it will be really brief. You mentioned that you're led to matrices over the Octonions, only to the 3x3 matrices or general matrices?
Well, what we've got here, when I was discussing the Wilson, Dreham, and Ode work, so here's 2x2 matrices over Octonions. All right. And then the Albert algebra, and presumably what happens in F4 is 3x3.
Yes.
I don't actually know, and Tevian or Karen may know better, whether one ever needs to go higher than that in terms of the dimension of the matrices over Octonions. I'm only aware of needing 3, but we'll see. I mean, my bet is the 3 are arising because of this triality. That this is the 3-ness that corresponds to the the Albert algebra. But I don't know that yet.
Okay, just a hint: if you happen to go beyond 3x3, strange things might happen as well.
Right.
So the part of Octonion matrices some people would call unhealthy. So they're very, very non-associative, so to speak.
Right, yeah. I mean, my aim is that I find it very difficult to work with things like matrices over Octonions. I'd so much rather have it, just ordinary STA operations, because I know how to do those.
Okay, so yeah. In any case, you can use the multiplication operators of these matrices, and then you back to an associative algebra. So
yes, but you need these special rules.
Yeah, true. Yeah, you're right, of course. Okay, I'm done with my questions.
Thank you. Anthony, I had a big picture question for the future. So on the one hand, we have particle physicists, phenomenologists, and experimentalists, say the LHC and Fermi Lab, studying standard model, beyond standard model, looking for breakdown, new predictions. Then we have our community on this algebraic approach to the same problem. Standard model, its unification with gravity, beyond standard model. What can we offer the other community potentially as predictions, which would, let's say, get them interested in our way of looking at it? As the way things stand, there's a gulf. They seem to not really take much interest in what we all are doing. Ashutosh is here. He keeps asking me, what do you predict that I can measure? So what is your take on you? Anyway, you are from essentially an experimental astronomy background. I'm sure you're very aware of that we need to offer something.
I suppose in terms of predictions, I feel, personally, a very long way from that. This is still something that's a matter of understanding what's going on. Can we explain what we see in nature? And generally, we've got more than enough data to go on already that needs explaining. I think,
I agree. When I say that, Ashutosh would say I'm making post-dictions. Where are my predictions? So I understand where they are coming from. I do think that post-dictions are also challenging because there's so much data has piled up which needs explaining. And I cannot call that just post-diction. It's like if Einstein explained the perihelion precession of Mercury, it's a good thing. It's not just a post-diction. So, Ashutosh, do you have any thoughts you like to add to this discussion?
Okay, can I just make a small counterpoint to your perihelion of Mercury point? There was a contradiction with an existing paradigm. So you get Einstein's modification or modified gravity explaining something that didn't have an explanation from the existing accepted paradigm, shall we say. That's not exactly analogous to what quantum field theory with its axioms and with its parameters, shall we say, a bunch of parameters and a bunch of axioms put together, already explains, and then you offer an alternative explanation. Small difference between that and the Mercury.
No, Ashutosh, what I would say is quantum field theory, for example, cannot explain mass ratios. At least hasn't explained it so far. Maybe we are offering you something beyond, which in fact requires unification of standard model with gravity before I can start being able to explain. I know not everybody agrees with my viewpoint, but I'm saying that some of this data, like CKM parameters and things like that, at least so far, it seems that quantum field theory is not able to explain that in that sense. For me, mass ratios are probably in league with the Mercury perihelion.
Fair enough. What, of course, the way I would paraphrase then your paraphrasing of my comments to you personally was the equivalent of the Eddington et al. Experiment in the Pacific.
Yes.
Yeah.
Yes, I totally agree. We are lacking in that, yes. In anything that we have done so far, as Anthony is saying, we are some long way or short way. We are not there yet.
Yeah, and as a cosmologist, of course, the problems are probably even more acute there, in that, famously, we can't explain 95% of the universe.
Right. Yeah, but I would say that's a problem of particle physics as well, isn't it?
Oh, yes. Well, the dark matter side, I agree. But cosmological constant,
yes,
that's pretty much something I think people working on the gravity side should, I think that's one of the things they should feel they need to explain.
I agree. Yes, there are some...
I might offer just a sociological in a way, me being part of the big field of experimental particle physics, I will admit, we could use some shock and awe. This is a purely sociological comment. Some feels complacent is the wrong word, but you ask how experimentalists think. It's if there is something which is computable and computes experimental observables that appear to pan out when you measure them. Most experiments will say, okay, it's good enough for me. But if you shock them with something that then doesn't work, or some experiment kind of is proposed on the basis of an alternate logic, suddenly you say, my God, that alternate logic is doing a better job. It has a psychological impact, which is not the same thing as saying I can explain CKM matrix elements and you can get rid of the parameters. That is fantastic scientifically, but it doesn't.
Yeah, I agree. So I think, but at least one could say, if some theory is beginning to be able to explain existing unexplained data, then there's some promise that it will predict something extra also.
Yes.
As opposed to a theory which is unable to even explain what is the already existing unexplained data. What predictions can I expect from such a theory?
Agreed. Yeah. I think that's a good way to put it. I would buy that. Yeah. I would say it myself somewhere.
Maybe I could just ask at this stage something which I think I asked you before when you were speaking about the G-2 experiment for muons. So that seems to me probably closest to being something of the type that you were saying just now would actually get attention. You know, if one could, if that firms up to be a real thing, then it will be extremely interesting to try and explain it. And what I wanted to ask is, given that I think there have been developments since we last spoke on this, do you believe it's any closer to being a real anomaly?
So now that is too tempting a question. I can't avoid advertising my own work, which is the other high precision measurement we do in high energy physics, which is the mass of the W boson, which also, at least in my analysis of my work, is showing a big anomaly. Now, there is a very interesting fact that some people have published, that the hadronic vacuum polarization correction that goes into the standard model calculations of both of these observables, which then changes the running of the alpha, the electromagnetic coupling, which is extremely precisely measured at Q square of 0, but then you have to run it up either to the muon scale or the W scale. And in that running, the non-perturbative contributions are the question mark. So where do you get those? The lattice calculations of those appear to be moving the alpha through the new hadronic vacuum polarization input in a direction where the standard model number of G-2 is moving closer to the experimental value. But at the same time, it moves the standard model value of MW away from the measured values. So there's a paper in Nature Communications that says, no matter what you do to the hadronic vacuum polarization input to the standard model calculations, you cannot get rid of both anomalies at once. Now, as it turns out, the lattice input is kind of getting rid of the G-2 anomaly, but enhancing the MW anomaly. So,
right.
So whichever one, there is something cooking is I mean, I'm clearly deep into this thing. So you asked a question that allows me to advertise, so why not? But anyway, something is cooking between the two. Shall we leave it at that?
Actually good news if you have anomalies that don't disappear.
Yes, maybe that's news.
Yeah.
So maybe I would like, sorry.
I'll get back to you. While on this question of anomalies, Anthony, I could ask you things about the cosmology side, little away, but important still. The Hubble tension, do you now take it as a serious thing? And the second thing, or the first you answered it, then I come to the other one.
Well, I increasingly pay attention to the Hubble tension, and I think it is serious. It's not going away. And, I know one side of it quite well, the micro background side. I certainly trust the people on the other side, the local distance scale, to have, spent a huge amount of time trying to understand if there could be systematics on their side. And these things are very difficult, but everything I've seen suggests to me that there is a tension. I mean, that it's real. And so I don't know if your other question is going to be about whether any of these theories help, but in fact, the ones I was talking about with the quadratic Lagrangians, which give you this background cosmological torsion, I said that it could start off at any value and gradually tends to a constant. It turns out that does affect things in the early universe. And in fact, it can affect them right through to close to recombination when the microwave background's being emitted. And it turns out that it simulates during that period, if this asymptotic movement of the torsion towards the constant value, it simulates a period of having dark radiation, as they call it.
So-called early dark energy?
It's not early dark energy, it's early dark radiation, and the invasion of state of this substance is not really substance.
Very interesting,
It's a third. And so it's as though you've got radiation there, and you can actually, it looks very possible. We mentioned this in one of the papers that I've listed. It looks very possible that you could have a different H back then from the one you see today because of the effect of this dark radiation.
Very interesting. Yes, great. Thank you. My other question has to do with the wide binary systems. The Gaia data, which has come in the picture in the last couple of years as tests of Newtonian gravitation versus MOND. Have you looked at this? Do you have a view on this?
Yeah, I have looked at it a bit, but I'm probably a month or two out of date. So a group up in St. Andrews, we're going to be looking at this using a Bayesian approach, which hadn't been used before. And what I heard is that the results then are a much closer agreement with Newtonian, but I'm not aware of the results having come out yet. This is just rumor.
Okay. I forget the name of the people. So there's Kyun Che from Korea. He is claiming it's more like MOND. Hernandez from Mexico also saying it's more like MOND. And there's a third group. I forgot. I'm not. So maybe you're referring to the third group.
Third group who are at St. Andrews, I believe.
Yes. Okay.
Yes. Okay. And so
but if it agrees with Newtonian gravity, it's bad news for MOND then, right?
That would be bad news for MOND.
Yes, isn't it?
Well, I do have difficulties with the MOND approach in situations like this, in the sense that it must be very difficult to figure out what background you should be taking. These are sitting in the potential of the galaxy. How much effect will that have? So the external field of the galaxy could be the dominant effect, who knows? And then you wouldn't be in a really low acceleration regime. I'm not sure anyone knows how to work these theories out, given these multiple layers of where the effect is coming from.
I just could add that on 24th November, we'll have a talk from Kyun Che of Korea on this, his results. So if you are there, it'll be great to have a discussion, because he claims to be able to calculate the external field effect on wide binaries, and then his claim is that the resulting effect is more close to MOND than to Newtonian gravity. But yes, he's disagreeing with the people you mentioned. His criticism of the third group of people was that they don't have a calibration. They were only doing the very wide binaries where the acceleration had already gone below the Milgrom level, whereas Hunche claims that he has a calibration from the not so wide binaries which are agreeing with Newton. So he calibrates using the binaries which agree with Newton, and then finds a departure for more wide binaries. But so maybe this group that you mentioned probably is now taking care.
Yeah, as I say, I'm a bit out of date, and I will try and find out soon, I think, if there are some new results, because I'm very interested in this. It could be one of the, most important things around if it's real.
Yes. But you're saying settling it won't be too easy because of the potential of the galaxy, for example. Yes.
And it's not just that. You have to make several assumptions about the distribution of various properties of the orbits, because you can only do this statistically. It's impossible to study the orbits of these very long period objects for real. You just have to infer it all statistically.
Okay, great. Thank you. Yeah, Bernd, please go ahead.
Oh, thank you very much, Tajinder. And by the way, I forgot to mention that. Thank you very much for the nice talk. Sorry, it was a little bit impolite from my side to wait to say this until my third comment. So I would like to add some historical remarks concerning the questions, how new theories arise. Of course, one way is that you have an anomaly which cannot be explained by the previous theories, and then you have to devise a new theory. But also what Tajinder said, one classical example is the move from Ptolemy astronomy to Keplerian astronomy. So the epicycles did explain a lot of data. You could calculate the positions of the planets very precisely, given the instruments of the time. But then a better theory came, which at first was not better because they still used circular orbits. But then this better theory explained the data in a more parsimonious way and made more new predictions. The same is true for general relativity. It did not just only explain the anomaly of the Mercury orbit, but it predicted new things like black holes or gravitational waves. Nobody would have looked for gravitational waves if you just take Newtonian gravity. So this could also be that the new theory explains old data and then also makes some radical new predictions. That's just an example I wanted to point out. And
I agree in the algebraic approach currently, such clean new predictions which are measurable are lacking.
Okay, of course, this is a problem for the algebraic approach, or for any approach which aims to get a new theory. So homework to do for the Octonionists, so to speak. And concerning the Poincare gauge theory with a quadratic Lagrangian, because you asked whether there's some relation to the weak or also to the strong nuclear force. Yes, there have been attempts in the 1970s and 1980s it was called, I mentioned this earlier in a previous meeting, strong gravity, where they used to apply torsion theories to the weak and nuclear forces. And it can also go the other way around. If you use the general Poincare gauge theory, you get features for gravity, which resemble the strong and the weak nuclear force. For example, you also get something like gravitational confinement, which might also explain the rotation curve of galaxy, or might be an explanation for non-Newtonian gravity in the weak limit. So it goes in both directions.
Actually, I thought
No, please go ahead.
Yeah, just on that point of the possible confinement and nonlinear effects, I have got a paper on that with Will Barker and Mike Hobson, and we show that the specific proposals which have been made for that do not work.
Okay, but this is also important information. So
yes. I mean,
thank you very much.
Many people have been interested in whether just with ordinary Einstein gravity, so general relativity, then whether nonlinear effects could be causing the flat rotation curves.
Mm-hmm.
And a lot of them focus on gravitomagnetic effects, which are certainly absent in Newtonian approach. But then there's other things like these sort of confinement effects and nonlinearities, which I think is particularly Durr, who's been the person advocating this.
Yes.
And in both cases, I mean, we've carried out quite a detailed study. We find the specific proposals don't work. And I find that quite reassuring, actually. I'm not sure I want Einstein gravity to be failing, or in the sense of not able to, the predictions we make from it, not working on galactic scales. I do believe that when we see these flat rotation curves, either it means there is dark matter, or it means we have to modify gravity. And I don't think we have the choice, from what I've seen, of saying, oh, actually, it's some effect in ordinary GR which we didn't take into account.
Okay,
I agree. I agree. Sorry, could I?
Yes, of course.
Tempted, yeah. So on just because the related remark, when you said that rotation curves might require modification of gravity, what we are looking at, because it comes from the E8 cross E8 underlying model, that the analog of electroweak SU2L cross U1Y on the gravity side is SU2R cross a U1 dark electromagnetism, where SU2R I am motivated to try to relate it to general relativity. And this U1 dark electromagnetism might be the underlying theoretical basis for MOND. We are just looking at it. And the good thing about having an electroweak-like structure on the gravitational side also is because this theory might be renormalizable as a gauge theory, SU2R cross U1 dark electromagnetism, for the same reason that electroweak is renormalizable, and the weak force per se is not renormalizable, for the same reason that general relativity is not renormalizable. So somehow this additional U1 in the gravity sector could be useful. It's like a fifth force. It's a fifth force. Yes, Bernd, sorry, I stopped you.
No, you don't need to be sorry. It was very interesting. And yes, so basically my comment was also related to modified theories of gravity, which have some features resembling the weak and the nuclear, the strong and the weak nuclear forces from the mathematical structure. So I was not talking about taking into account effects from ordinary general relativity, but I mean some kind of Poincaré gauge theories which have features which resemble the weak and the strong force, and also have some kind of confinement. It would be interesting to know whether the general gravitational theories also fail to account for rotation curves, or whether there are some problems. And if I recall it correctly, next week we will have Matej Pavic.
Yes.
So maybe for Professor Lasenby, it would be interesting also for you to listen to him, because he has some very unconventional ideas how to make pathological situations work. So how to deal with ghosts and even tachyons in a way which does not necessarily require to discard them. So maybe this would be of interest, because okay, this is a very strange fear, I have to admit. I have that maybe we are trying to get rid of bugs which are actually features. So maybe there is a theory of gravity which nicely explains dark energy and dark matter, but we might have to swallow something up, so give up some of our old concept and deal with unconventional features then. It might not be true. So it's always better to have a more conventional theory, so you shouldn't go too much into the speculation and radical change direction, but maybe this could be something which we overlook. That's why I think it's interesting also to look at people who think we might also make very exotic work.
Yes. Regarding rotation curves, so I don't call this a need for modifying gravity, but rather a fifth force which dominates at very low accelerations. So on the astrophysical scale, if I have two clumps of baryons, not only do they attract gravitationally, GR/Newton, they are also experiencing another force which at low accelerations dominates GR or Newton and looks like MOND. So the analogy is that if I have two electrons, they have the electromagnetic force as well as the weak interaction because of two different charges. But in a similar spirit, on astrophysical galactic scales, there are two forces: gravity, which is like the weak force, and then there's an analog of electromagnetism, what I'm calling dark electromagnetism. So instead of having to add dark matter, I'm having a fifth force, which is enhancing the gravitational attraction of two stars at very low accelerations.
And what would be the charge or force of
The charge is square root of mass. You remember from our earlier discussions. So the four current analogous to the Maxwell current is the moment root m times ui is the momentum, quote unquote, momentum of square root of mass.
Okay.
GR is sourced by the energy momentum tensor of the mass. Dark electromagnetism is sourced by the four current of square root of mass.
Thank you for reminding us and me. Okay, and do you have any comments on my how do I say it on the idea that we might have to take radical measures in some sense?
For me, I think whatever you're asking, Anthony or me.
Both of you, or maybe maybe also the experimentalists.
Yeah, in my view, what we are doing in the algebraic approach, in my view, this is already radical enough. We are trying to describe fundamental states using new number systems, which seem to have additional properties which were not there if you did not use these. That's how I am looking at it. But Anthony, you may want, and Ashutosh.
Yes. Well, very similar. I think it's very good for people to try more than one approach, and you have to work on the basis of what appeals to you and what seems to be most likely to be something new. And to me, the Octonian approach, it really has the feeling of something new and different, and which has a chance of getting somewhere, because it's all to do with geometry and patterns that pretty certainly underlie what's going on, and we have to work out those patterns and the geometry.
Okay. Thank you. So I have no additional questions or comments. But the experimentalist wants to say something.
Tejinder, maybe my comment here would be, we also need reasons to improve our experimental technologies by large factors. I mean, my statement about any new accelerator facility or any other experiment one does, conversations tend to start with the science case. What might you develop and what might you observe and what new discovery might you make? But that's in the hands of nature. The experimentalists are, I think, more responsible for answering whatever you're proposing to build in various metrics, how much better are you able to probe nature than before? 10 times better, 100 times better in some metric or the other. And if you make that kind of a technique advance, then it's worth the effort. If you can make that kind of an advance, then you may have predictions for us or you may not have predictions for us. We hope you have predictions for us. But if you can make some technical advances that are so big, some order of magnitude kind of thing, then you give nature a chance to reveal something that couldn't be seen before.
Perfect.
That's good enough. That's the way I would.
I'm recalling from your recent colloquium the luminosity frontier as opposed to the energy frontier, which looked like a doable project in the next few years and which might be carrying fairly important information.
Some weak signals, weakly coupled things, maybe of the kind you're mentioning, produces a small signal, but it creates enough of a deviation that you can observe it. So I would also advertise Fermilab's extremely intense beams which could also be used to observe some small, maybe some signature of your dark photon or something. And in fact, there we have capabilities, and maybe we can develop more, which in some sense is missing a science case. But our argument would be we should go ahead anyway, because who knows what surprises might be in store. Whole bunch of physics showed up because somebody looked in a place in a new way that nobody motivated anything, but something interesting happened. So this whole thing about science case going first is fine up to a point.
Okay, I see what you're saying. Yes, but definitely for us to be able to get experimentalists interested in what we are doing, you expect us to predict something measurable. That would make a bridge between phenomenologists and experimentalists and the algebraic people on the other side.
Yes. My sense of the sociology is if you explain things that the standard model doesn't explain, your audience are the standard model phenomenologists, or shall we say the quantum field theorists, or that's your audience. Yes. It's between all of you. The experimentalists at some practical level are saying, what should we do next?
Yes.
Which technology should we push next? And so while we are all scientists, we know better our own business. If you explain the CKM matrix, which CKM does not, at first glance, it appeals to other theorists, perhaps. It still doesn't say what an experimentalist should do.
I agree. I totally agree. Yes.
So in that, it's as I said, it's a more sociological comment rather than scientific. But to get experimentalists involved and excited, you say, if you can build this thing, I say you will see a new phenomenon or an anomalous phenomenon.
Absolutely.
Then you get all of us fully excited and saying, how can we figure that out? How do we build that thing?
I mean, but this has happened before. Once again, the nice example is general relativity. Einstein explained the anomaly in the orbit of Mercury, but he also predicted that starlight will be banned by the sun. And then there was this expedition. And so normally if things work out, it rarely happens that you have a new theory which just predicts old stuff and doesn't predict anything new. So I would guess if we have if the Octonionists have figured out how to make predictions for already existing stuff, they will also give us some new predictions where we can look at. So
I expect exactly.
One thing follow from the other. So
that's a very good point.
So it will open the door to new discoveries if you're able to make predictions and explain also unexplained or, let's say, pure numbers which cannot be derived from quantum field theory. I would guess that will also open the door to new discoveries, totally new discoveries, once we are at this point.
We have a comment from Tony Bell, who hasn't spoken before. Would you like to please say it out so that we can discuss it?
Okay, can you hear me?
Yes, please, go ahead.
I'm a machine learning researcher, but I got interested in this field because I've been reading about Clifford algebras for about 20 years from Anthony's books and papers and many other people. And I'm also very interested in this approach to physics. And I just made that comment because the discussion that you're having with Bernd there is related to the idea in machine learning that you have two terms in your loss function or your objective function. The first being how well you explain the data, and the second being how complex the model is. And in the Bayesian approach to machine learning, you have both of these terms. And if you just fit the data the way the standard model kind of looks like they've just banged together a bunch of gauge groups in a way that we don't understand, But if you made a simpler model where all those gauge groups came out of a larger theory, the way that you're trying to explain the thing, that corresponds to reducing the model complexity term, which is the second term, which is the Bayesian term in the data fitting, and sort of canonically, when you reduce the model complexity, you have a thing that happens, which is that you generalize better on the on unseen data, which would be experiments that you haven't done, and so on. And therefore, the model complexity reduction is intrinsically related to making better new predictions because you're generalizing. That was all I was saying there.
I agree. We agree. So the kind of question which has been asked to many of us is there some effect for which we can do the QFT calculation? You do the same calculation in the algebraic, octonionic, geometric algebra approach. And can you do that and get a different number so that we can test? That's the analog of bending of light. And we are still sort of groping in that direction. I was telling Ashutosh, we need a particle physicist, maybe a phenomenologist, to take interest in this approach, because they are more used to G-2 W mass anomaly. They will be able to help by telling us what we might be able to calculate from here, which could be compared with QFT. So many of us don't have that feel right now here. If you ask me to calculate G-2 in the octonionic approach, I have no idea right now how to do that.
So you think you would have to team up with a phenomenologist?
Yeah, no, the teaming up requires an interest on their part to understand how this stuff is done. Just as we are trying to learn phenomenology, they have to say, okay, I will learn geometric algebra and octonions, but that motivation...
I see. I mean, that's the problem. You need something to get started before you can get started.
Yeah.
You need a phenomenologist to get interested so you can make predictions which make the phenomenologist getting interested in the first place. This is tough.
Then you have to be Einstein. Yes.
Yeah, otherwise, okay. But there wasn't a... Yeah, sorry. Go ahead.
I think you guys are extraordinarily close to a massive reduction in model complexity, actually. And if you achieved it if you really fitted all your geometrical groups onto the states, the representations of the particles, at that point it's game over, because the rest of the stuff will just flow out. If you get that unification, I think that it will revolutionize physics.
So you mean if it works out perfectly, we will not need a phenomenologist because everything will follow from the theory?
Yeah, I think that's what will happen. Yeah, and you'll have new predictions.
Yeah, we will have new predictions. At least in my limited sphere, I'm saying, if we make a theory which explains current data, the theory is coming and saying, I'm predicting something which must exist. Because I explained this, I have new prediction, like a fifth force which mimics Mond, or a second Higgs maybe, or that the Higgs is composite. Such predictions are there, but they are not quantitative. They are not a number.
Yeah, but the things that you and Rob Wilson are getting with the mixing angles and the various mass ratios, that's so close to the level of the kind of thing that a prediction would be. I mean, those are unexplained things,
Yeah, I agree. So what we would need to do is, related to that, come up with something more, which would, as Ashutosh said, shock and awe. That, that this thing must be there in the LHC at this luminosity. You please go ahead and look for it. You will find it. That kind of confidence. That last bits of not yet, but thanks. I agree. It's very encouraging.
I think the most likely thing that would happen would be the unification with gravity, because you know, you're getting close to understanding the three generations of the masses of the particles, and so that goes directly into your discussion on Mond. I think that the dark matter thing is probably just a sort of tectonic shift in the quantum field theory formalization. And that in that respect, actually, it's something that hasn't been mentioned. Two things that haven't been mentioned in the talks I've listened to are the first is a kind of a direct action approach in quantum field theory, where you're sort of calculating the Green's functions between particle interactions rather than having this massive number of multiplicated fields inhabiting all of space-time, which is a hugely redundant structure from the point of view of, say, information theory.
And very
and I'll just finish. And the second point is that another community I've been following that is very interesting is the positive geometry people, the scattering amplitudes community that studies these geometric amplituhedron structures, which is more closely related to the S matrix approach in quantum field theory. And these are very interesting. I mean, they have got a lot of beautiful geometry in there, a lot of beautiful projective geometry, but they're usually operating in very simple field theories like scalar, scalar phi cubed theories and so on. And so I would imagine that what might happen is that the more complex algebras and geometries that you're studying would go together with the kind of geometrical structures they're using to compute amplitudes, which are very close to Clifford algebra structures, actually, in terms of using the meets and joins of various tetrahedra that tile the surfaces of these things that they compute the volumes of to get the amplitudes. So those two things are things that I would see as being likely avenues of.
On this second point, I find it curious that the amplitude hadron people probably are not interested in the Octonions or in the algebraic approach, and I don't understand why they don't find these ideas more also interesting.
They're not interested because nobody can compute anything new. And any of these working with Octonions mathematically is pretty difficult. And even if you create a theory that's uniquely in the Octonions and it gets the standard model, I mean, who has even computed classical tree amplitudes with Octonions yet? So what would need to be done to excite those people is to develop a spinor helicity formalism. For instance, there is a 10-dimensional spinor helicity formalism in the literature, and there's a 6-dimensional one, and it's very obvious that quaternions and octonions would clean that up. I started doing this years ago, but never really finished it and just haven't gotten back to the problem. But also the Clifford algebra community could develop a spinor helicity formalism, which exactly allow for inner products of spinor solutions. And then once you have that, then you could do scattering amplitudes in arbitrary dimensions in a very helpful way that might allow for efficient solutions. But typically, yeah, I mean, even working with octonionic matrices has been very difficult until very recently. So it's just very difficult to compute anything with these things, especially division algebras.
I think it would be reasonably easy to turn the spinor helicity formalism into Clifford algebra structures, actually. And it would be much more elegant than the way that they're doing it.
Yeah, it's probably totally doable.
I would like... Oh, sorry. Go ahead, Mr. Cotwell.
Just a quick comment. Even if you cannot be quantitative just yet, and we've just heard maybe how you get there, but even if you're not there yet, the LHC is a top quark factory and it's a Higgs factory. So even if you made some qualitative predictions that you expect the top quark to be partially composite, or you expect the Higgs to be composite, and you expect certain kinds of final states to show up in top quark scattering or Higgs scattering or any such thing. Even if you couldn't predict rates or you couldn't predict energy scales, just saying watch out for such signatures is already a step forward. Qualitative predictions are fine too for now, for starters.
So, David, it's not as bad. Like, there are certain signatures coming out. We can't do QFT calculations, but at least we see some hints about beyond standard model physics, which the particle physicists might be interested in.
You could just write those down and
yes,
something for us to discuss at our conferences and stuff like this.
Right. Okay, so
Hillary C wants to say something, I guess.
Sorry, who is it?
Hillary.
Okay. Please go ahead. Please go ahead.
At least it looks like the hand is raised.
Like, oh no, okay, so maybe someone not showing up on my, no.
Okay, then it's a mistake on my side.
Should we be winding up or more discussion? I think
it was not him. Okay, sorry.
You're really tired, Anthony. 3 hours. Thanks so much for bearing with us in this marathon.
It was terrific.
Terrific, and thank you very much.
Well, thanks very much to everyone for listening.
And good luck with your papers and your project.